FRB is associated with NIR1, then it rules out an isolated magnetar channel. Yes. Okay. Good. So the question is. Great.
Yesterday, there was a question about fallback disk and what kind of infrared emission they make. So maybe isolated magnetar, I don't know, could it have a fallback disk that's been hypothesized in the past? Maybe not totally ruled out. That's all I want to say. Thank you.
Great. So let's consider the cases where there are some other periodicities seen from some FRB sources. So, for example, periodicity seen from in the rotation measure of some bursts, at least claimed periodicities. So the question is whether we can conclusively establish the requirement of binarity in magnetar engines to produce FRBs, or whether we can observationally say for sure from some sources that a fraction of these FRBs do not have binary companions. Is that yes? So yeah, the first question is on binarity, whether observationally we can put some constraints on what fractions of FRB sources, if powered by magnetars, are a part of binary systems and not. There are some other post-galaxy properties and some other theoretical constraints, for example, based on population synthesis simulations, that suggest that of the order of maybe 10% of magnetars could be in binary systems, could be in binary systems. Can that be confirmed with FRB observations, potentially by JWST follow-up of nearby FRBs? Can that put some constraints on the theory? And we had a really nice talk by Junshuo Zhang yesterday on this hyperactive repeater, FRB 240114A, that has been emitting about 10 to the 47 erg or so, which is comparable to the magnetospheric energy in typical 10 to the 15 Gauss magnetars. So is that really a problem for magnetars, or can we circumvent that through some other channels? There were some really nice ideas put forth by Mr. Rauer and others on Slack yesterday. So is this really a problem or not? And do we need alternative scenarios? Are there any evidence for them? Are there any hints for alternative scenarios, say interacting white dwarfs or flaring black hole jets or whatever, and the observational constraints associated with them? Yeah, so these are the questions that we have for the first topic. Let us know your thoughts. Sorry, Elias, do you have anything else to add to this?
Okay, so I think one thing that, I think was already addressed largely yesterday, I think there is a lot of, I think, good synergy with those galactic mimickers, especially as you mentioned, the effects of binarity. Can you have like mode conversion in a companion magnetosphere? So I think even though the systems, as you say, may be different in terms of the physics that's operating, in terms of how relativistic they are, by and large, I think we can check for the existence of periodicity. And I think we'll see that also later in the discussion when we talk a little bit about other counterparts that we could expect, that we can use those systems to learn something. And I think that's something that I find also very exciting.
Mm-hmm. Any take on any of the points here? Do you want to add a few words?
So there's a galactic, is Aurora already seeing University of Maryland, Master Goddard? So there's a galactic center magnetar. Presumably there's magnetars in other galaxies near their cores. So do we see that? Why don't we see it? Is there some bias? Yep.
Shami, please unmute yourselves.
Yeah, I had a question more for the theorists here, I guess, about this idea that the burst storms might lead to the magnetar energy being exhausted and there being a larger reservoir of magnetic energy deep in the core of the magnetar that can be brought to the surface. Um, is there any idea of what the limit on that reservoir might be? I mean, at a certain point, we're going to run out of that reservoir as well, right? Or is that thousands of times larger? I have no sense for that.
There's a limit on stability of the neutron star of about 10 to the 17 Gauss. So that's the physical limit, I guess you could say, of the reservoir.
Can that be have to produce FRBs or not? If it's all buried in the community.
I mean, that's an open, yeah, we don't know.
So, but that's 2 orders of magnitude. And then there's also the field volume, I guess, but that's not necessarily any larger than the magnetosphere.
Well, right, it's the limit is basically the gravitational binding energy of the neutron star, but a few, like tens of percent or 1% of that is your magnetic energy reservoir that you could possibly ever tap.
Alex, feel free to unmute.
Yeah, I guess just on this point, all of the kind of estimates of how much energy you're depleting depend very sensitively on what your radio efficiency is. And currently, I think most of the works assume this is 10 to the minus 4, 10 to the minus 5. These constraints get much weaker if you have more efficient radio emission. So we know one source, SGR 1935, but we don't know whether fast radio bursts from hyperactive repeaters could be much more efficient in their radio emission, for example.
Yeah, I would just add that in that presentation, the field that was assumed was 10 to the 15 Gauss. And we routinely have measured through spin down, in the standard dipole formula, 10 to the 15 Gauss magnetic fields for some magnetars. And that's just the dipole component. So that really is just a lower limit, even for the surface on the field. So I think this point's really important.
Yeah. Also some comments for the energy budget for the magnetar. So even the hyperactive repeating FRB source 2024 0114 has shows maybe a challenge the energy budget for the energy budget of the dipole field of a magnetar, but there are still some free energy can store in the magnetar, such as the toroidal field can exist. So it can store much more free energy. So maybe more larger can. So I don't think it's actually the observation for the active repeater can actually challenge the energy budget for the magnetar.
Are there any inner magnetospheric emission models that can tap into the quadrupolar fields, for example, to produce FRBs? That is, if you run out of the 10 to the 15 or b square r cube, taking 10 to the 15 Gauss, would you still be able to produce FRBs by tapping the magnetic energies? Is that possible?
Do you have like a good model for to tap into the dipole like component of it?
Some might.
I'll do mine first. This is Robert Main at McGill. I just wanted to ask some people to maybe quantify some comments about there's a vast energy reservoir from the non-dipolar components or from the twisted fields. I would love to know is it a factor of a few? Is it an order of magnitude? Is it several? Could anyone answer how much energy there might actually be?
So is it safe to say that there is no prediction from the magnetospheric model so far on the amount of energy that can be tapped into FRBs? Could you take the
It would be some small fraction of the gravitational binding energy of the neutron star, right? So depends also on how efficient the radio emission mechanism is and how collimated or beamed it is. So it's the apparent versus the true.
So after this comment, we'll quickly take one additional comment on the issues with binarity, and then we can move on to the next one. Yeah, just after this. Yeah, Vicky.
So I also just feel, because he's not present, but there was a very well-known magnetar theorist named Andrei Belaborodov from Columbia University, who, if he were here, he would be quoting his paper from 2024 that says it's impossible to get FRB luminosities out of neutron star magnetospheres because those luminosities are damped in the magnetosphere no
Next
matter.
slide.
Yes, that's the next slide. Never mind.
Yes, Wenfei Yu, can you unmute yourself?
Hi, this is Wenfei. Can you hear me?
Yes.
Okay. So actually, I'm talking about the 2024 01114A, and I would like to remind that the counterpart also, when we consider the energetics, we also need to consider the energetics for the counterpart, and that might be much larger than the bursts. And we have to consider that the source of that in order to understand the energetics for the repeater. And this one thing I would like to remind, we need to consider also the energy for the counterpart. The other thing is that, as we mentioned in some of our papers, we also mentioned that some kind of newborn sources that may be not that people theorists usually consider, for example, just a magnetar or just a millisecond pulsar. But when we realize that maybe when the systems are newborns, then the situation may be more complicated. There's also additional energy in the system. So I think that might be. So I want to hear ideas from the theorists here and the possibilities. Yeah, that's what I would like to comment and ask.
Thanks. Would anyone like to comment on that? Yeah.
Yeah, I think before we
Would you introduce yourself?
We are from University of CS. Before we discuss the energy budget here, I think we should first consider several effects that may influence the energy budget calculations, such as the beaming factor, duty cycle, and effectivity. So a beaming factor also includes the individual beam factor and the global beam factor. So before we consider that, maybe the energy budget, the energy budget here, we calculate we measure directly from the observation, maybe not the truly energy budget from it's not a truly physical energy budget here. So I guess the strictly upper limits for magnetar is the gravitational energy, the total gravitational energy here. So if if one day we observe the FRB's energy budget is larger than the total gravitational energy, maybe we tend to maybe 10 to 43 or to 42 ergs. So it would be rule out. I think that would be rule out the magnetar case.
Okay. So just a final opportunity for anyone, if you'd like to weigh in on the effects of binarity. Yes, please. Marcus Lowe.
Hi, Marcus Lowe from Swinburne University. I guess a really quick comment on effects of binarity. I don't think I've seen it mentioned in this conference, but there is a system called the double pulsar. Some people may have heard of it. One of the interesting observational aspects of that system is that it displays eclipses, where one of the neutron stars gets eclipsed by the magnetosphere of the other pulsar. And when it goes through eclipse, we see some absolutely incredible propagation effects, especially in more recent high signal to noise meerkat observations. Some of which, could be related to what's going on in like FRB progenitors and tight binaries with like another neutron star, or some other stellar companion with a pair plasma filled or just plasma filled magnetic field. So I guess that's kind of also worth thinking about. And we have some really cool data from meerkat on that.
Right. Agreed. Thank you so much. We will have to move on to the next next topic. Oh, there's Susana Araujo. Could you unmute yourself?
Hello, how are you? I was wondering regarding the multiple component of the magnetic field of magnetar, is there some model or something that we can observe to be able to estimate the magnitude of this component? Because we can estimate the dipole component, but I haven't read anything about how to estimate the multiple component.
So I think we raised a similar question earlier, and I don't think we have a specific answer to that, except that we could tap in the buried magnetic fields somehow, and then buoyantly raise them out to keep replenishing the lost energy. Okay, if there are no other follow-up comments to that, I'd say we move on to the next question, which is related to what we have been discussing so far. There are a few more questions, but if there is anyone who has a comment on any of these questions, we can take, but okay. But we also have a few more slides to go on. Jason, or
So Brian Gainsler, UC Santa Cruz. Just on your fourth bullet there, just more on the whether these hyperactive sources can exhaust their energy. So I was just chatting in the Slack channel. So if these things are beamed, but there's just as many beamed away from us as beamed towards us, then I think the energetics will cancel out and the problem's there. But if these are pencil beams, then the energetics problem goes away. So the question for the polarization, perhaps the pulsar polarization experts, is does the rotating vector model that at least some FRBs seem to support, does that require pencil beams, or can it also work with fan beams? Because it seems that the energetics question really comes down to what shape the beams are. And if the polarization can say that the beams are pencils, then the energetics problem goes away. So I don't know if anyone has looked into this. I don't know much about polarization from fan beams.
Jason, do you want to respond to that with your question, comments? Or okay, it's unrelated. Okay. Jason.
So I have a somewhat different point. Sorry, Brian. I don't think I've heard anyone mention like the Jupiter-Io interaction at this conference yet. So Jupiter and Io have a magnetic interaction, and actually, sorry,
the electron cyclotron.
Yeah, exactly, and it's the only example of an object that is actually brighter than the sun at very low radio frequencies. It's the only object in the sky that is brighter than the sun, and is not true anywhere else in the electromagnetic spectrum. And we've seen from some of the LPTs that they're magnetically interacting, and we can see them to much larger distances, right? There have been a number of FRB models that suggest magnetic interactions of white dwarfs in very short orbital period systems. Like there's a Mottez and Zarka paper. I think there's a couple of them at least. Could well happen with neutron stars interacting magnetically as well. So yeah, I think it would be good if we are not so myopically focused on magnetar models,
Agreed.
because I think we have like evidence in our solar system
Yeah.
and in our galaxy that this is not the only way of making coherent radio bursts. But I hear magnetars mentioned quite a lot at the conference.
Agreed. That was the idea of the slide that we should think about.
Okay.
Okay, I think we should definitely move on to the next slide, which is related to what we have been discussing on what theory can provide. There have been substantial advancements over the last few years on numerically simulating the magnetospheres, on how waves can be launched, how waves propagate, what's the nonlinear steepening effects, and how certain particle energization method can happen, and so on. And there have also been advancements on these nonlinear propagation effects, high amplitude wave interacting with the plasma inside the magnetosphere. There have been some theories, for example, Andre's work that Vicky mentioned, that suggests that these FRB-like waves cannot escape from within the magnetosphere across the field lines. So there have been lots of advancements made, there have also been some advancements in understanding some crustal properties of neutron stars that Elias will take over very soon. Just quick comment on the top right panel. The weighting distributions, for example, from repeaters, they don't always follow a log normal distribution. So do they all arise purely from magnetar crustal quakes? Can the weighting distributions, burst arrival times, be used somehow to understand the magnetar crustal properties, or whether that could be used to discriminate the underlying emission surface, emission engines? Elias, would you like to add more to this?
Yeah, absolutely. So I wanted to touch on a number of points connected with this. I think you've seen throughout the conference in several talks, including Navin's and Alex Cooper's talk this morning and many others, there has been substantial advancements, both in terms of the theoretical modeling of emission mechanisms, but also in terms of the global modeling of those systems. And two of the things I wanted to mention, and I probably just jump right to the image that we put there, is we can even ask a different question. We cannot just ask, what kind of emission mechanism can explain a certain observation, but also we can ask what actually at the source triggers the emission in the first place. And we heard a lot about this earlier today, about the impact of crustal physics. And what I wanted to show here, just to give you some example that this problem might be actually even more complicated than what we thought, is what would actually happen in this case, what is shown in the simulation, if we simulate a realistic star quake. So what's being done here is we took, this is work done by a visiting grad student here at Caltech, Louis Bernard, and also by postdoctoral fellow Ashley Bransgrove in Princeton, and myself. The idea being, we took a realistic elastic mode calculation for a star quake, and then we just injected that into a magnetosphere, because what we wanted to know is most of the insights in terms of in part both damping, but also in terms of those simulations of nonlinearity come from simulating individual pulses, and we wanted to know if we actually had a realistic event. So if the source in kind of an end-to-end modeling approach would tell us what exactly the injection is, what would the realistic feedback be? And what's shown in this figure is literally what that looks like. On the top, you see, basically you can think of that as being the alpha wave component. On the bottom, you can think of that as being the fast near-sonic component. And the situation is really complicated because effectively, if you think in terms of the talk earlier today, that there might be multiple chains of things being triggered, we basically see almost all of them potentially being active in the system. So we do see the formation of monster shocks, actually multiple of those. We do see the formation of current sheets. And large plasmoids, which you might be able to spot near the sort of equatorial plane of this figure. And even more so, after you have a continuous injection of all of those waves into the magnetosphere, you actually open up the dipole. So this is a non-rotating system, but then the nonlinear part rips everything open. And what you end up is a very complicated, twisted, distorted split monopole configuration. And on top of that, I think you would expect multiple of these mechanisms to operate. There's a periodicity in terms of the injection, and is really, really complicated. But on the other hand, what those simulations can also tell you, and I think there's a lot of opportunity there in terms of understanding what the source model can predict is not all of them have the same kind of energy in them. Even though you start with a fixed energy at your stellar surface, maybe only 1% ends up in the alpha waves, and a few more percent actually predominantly end up in fast waves. And so that, in addition to possible constraints, observations we heard for those hyperactive sources in efficiency of the emission mechanism, could give you a constraint of which one is favored and which one is not. So I think basically theory in terms of source modeling can meet also data right in the middle. So I think there's a lot of opportunity to be learned there, both in terms of, as we say, duty cycles, like at which point, can the system recover and then trigger another oscillation, or even if you have proper plastic modeling, or even if you model diffusion time of the magnetic field outside of the star, as we've discussed. And I think efficiency constraints there might also help a lot. And the nice thing is, what I want to say also on that slide is, this type of modeling has also been done for other systems as well. Like we had this question about Jupiter-Io interaction. And the nice thing is we can do exactly the same thing for the system, which actually for Jupiter has been very extensively studied, just because you have also strong observational constraints on the radiation belt dynamics. But also, for those systems here, we've done investigations of binary magnetospheric interactions for neutron stars, and you can put constraints on even what emission mechanism arises from the binary dynamics itself. So even the fact that, if you had a binary, would already constrain what kind of emission mechanism is favored from the dynamics. And so by kind of, studying the source properties, we can also get complementary constraints on those. With that, I hand it back to Navin to handle the questions in the room.
So Jens, do you have comments? Yes.
Yeah, hi, I'm Jens Malmann from Dartmouth. So I want to add just to this beautiful overview. It's actually not just efficiency on the emission side, but also efficiency of the propagation. So even before that converts to gigahertz waves, there's a lot of exploration going on what kilohertz waves actually do in these intermagnetosphere, how they might be damped, how they might shock or not shock. So actually is a multiplication of efficiencies, even if
you focus on emission. Exactly. And the thing is, in this is a very good point, Jens, and especially in this simulation that we show, right? Even ripping up the magnetosphere, in this case, going from a dipole to this monopole, drains a lot of the injected wave energy. So overall, when we look at this, we have only efficiencies of less than 10% that actually ends up in the wave that can potentially escape or not, which is then the different question. But you lose out a lot of energy, even close to, to the nonlinear dynamics that Jens was mentioning. Yeah, that's a very good point.
Yunhong, would you like to unmute yourself?
Okay, can you hear me?
Yes.
Okay, thanks. I want to follow Elias' points to add 3 comments. So the first is, Elias just said, we should not just care about what kind of model can explain something. I just want to add one thing is we should also check every models to look at what these models cannot do something. For example, just observationally from all kinds of diverse morphology, we see from the repeating FRBs, we know these FRBs are highly linear polarized, and the sunbursts are also highly circularly polarized, which means we need both X mode and O mode produced at the emission regime, of course. And we also see from repeating FRB, most of them are narrow spectrum, which means the relative bandwidth is extremely small. So this actually can put some very serious constraints, just like a scintillation. We can, based on scintillation to constrain the emission size, we can also use this bandwidth to constrain the different predictions from magnetosphere and shock. Second thing is, one thing we can do is based on different emission mechanisms to look at the efficiency of how many magnetic field energy convert into the radio. Actually, you will see different models really predict very different efficiencies. Just to look at the shock model, it's roughly 10 to the minus 3 divided by the magnetization. So larger magnetization you have, the lower efficiency you have, because the particle will take less energy if the B field is very high. But in this case, the sigma is very high. You will mainly produce a linear polarization. There is no circular polarization, and the flux will also drop. So this is like a drop back things. And you increase something, actually this will also cause you some very different observations. The third thing is propagation. After you trigger FRBs, can this FRB propagate? So I think this is related to two different questions. The first is like Andre calculated whether the FRB can escape or not. I also have a paper with Paul and Bing. We found as long as in the open field line region, the FRB is propagating nearly aligned with local B field, and as long as the plasma is relativistic moving. So we found the optical depths will drop. Okay, so this is like a one test particle, how this particle modify the cross section. The second propagation is just Navin mentioned, the monster shock. The fast mode, there is no monster shock for FN definitely, because E square is always smaller than B square. The MHD is always valid, but for fast mode propagation, just several weeks ago, the Alex Chen has a new paper on this topic. He found it's very easy to produce a monster shock at the quasi-perpendicular propagation, but as long as you the K is more close to the B, so you need to go to a larger distance to reach the E square rather than B square. And in this case, actually the plasma frequency is also dropping. So it's very hard to produce monster shock in the, they found a critical angle roughly at 50 or 60 degree. I don't remember correctly, but I still want to mention this. There is no problem in the open field line region. Okay, I think that's all I want to say.
Thanks, Yunhong. Yeah, so Yunhong's response was that FRBs could propagate along open field lines, but the okay. So yeah, there are a couple of other questions that are left here, which we can quickly explore before moving on to the next slide. Yes, Zoravar.
Okay, so I think we have to be a bit cautious of extrapolating what we know about normal magnetars to this sort of simulations. I think this is a Force-free or MHD type simulation, right? And it's unclear if that's sort of like you could have a very vacuum-like magnetosphere, perhaps a very slow rotator or something just very benign, and then you have a quake, right? And in that case, you'd be very far from this MHD limit initially anyway. So I'm just wondering if these sort of MHD type waves is what will be actually realized in nature, or maybe it'll be realized, but maybe this would not make an FRB. This would be something else.
Mm-hmm. And what's the multiplicity that you have in mind?
You would have basically a vacuum magnetosphere to start with, or something very very low charge density, and then you'd have a quake. So it's inherently a kinetic problem rather than MHD.
Yep. Thank you for that point. Makes sense. What specific predictions do observers want from theorists? Any quick predictions, especially from these kind of simulations of perturbing the magnetar crust, for example, or any other predictions from emission simulations that observers want from theorists?
One thing that I guess it hasn't really come up, but we found people have noticed some FRBs have microstructure, and some don't, and partly could be because of scattering. But there's cases where it doesn't look like there's There's not clear evidence for scattering, and yet we don't see microstructure. So I think, why sometimes do we see that? We don't. Is that emission mechanism dependent? How often might we see that? Is that a geometric effect? There's, I think.
It could be a combination of many effects, I think, including these nonlinear propagation effects and the onset of various plasma instabilities upstream of the propagation of the FRB waves. So that depends a lot on the upstream temperature, magnetization, the luminosity of the burst, and the density, composition, and so on. So it's only natural that you do not see that for all bursts, and because you do not expect the conditions to be the same, and the properties of the burst are not the same. So depending on these luminosity, for example, or the wave strength parameter and various nonlinearity parameters, these instabilities could kick in, which could give rise to various temporal structures onto the bursts. I think that's right now on a theory front is very much under exploration, but anyone can add their thoughts on this, on Vicky's question on why we see these temporal structures in some bursts and not in others. These microseconds of structures and shorter, for example. Yes, Kenzie.
Hi, this is Kenzie Nemo from MIT. Just to add to Vicky's point, I guess I have the same question, but also if there's timescales that are interesting, like for example, the circular polarization in some repeaters, you see it changing from 100% linear to close to 100% circular in short amounts of time. And then similarly with the microstructure, you see bursts that have it and don't have it. But yeah, that's on very short timescales. You see that change. And if it's propagation effects, do we expect it to change that quickly? Yeah, at what point does that start to become constraining?
Thank you. Yeah, good questions. Laura?
Yeah, I mean, as an observer, I would say everything, but maybe as a complementary dimension to what was just mentioned, I think all of these properties as a function of frequency would also be extremely useful. Now that we have these nice wideband receivers, we can not only probe sort of temporal dimensions, but also the frequency aspect of things like burst rate versus frequency. How does polarization change with frequency? How does time scale change with frequency? That's actually a pretty straightforward thing to measure. Things like this would be emission bands as a function of frequency is also a fairly straightforward thing to measure. So that'd be useful. Sorry, I forgot to introduce myself. Laura Spittler, MPFR.
There's one online question.
Yeah, I just had a quick comment. I just wanted to say that the predictions for IR luminosity to test with JWST imaging for nearby hosts might be useful. Maybe it could even lead to a nice JWST TOO proposal. So just saying, just wanted to put it out there.
Jason?
Yeah, Jason Hessels, McGill University. So regarding your question about predictions, I guess one thing that I wonder about is, if we had radio telescopes to search for FRBs at 10 or 20 gigahertz or so, is that going to be a great boon for our science, or do we expect theoretically that the beaming fraction will become narrower and narrower, so the event rate goes down and down because these are shooting past the Earth instead of hitting it? Or could that be compensated by having just more energy at those higher frequencies? I haven't heard a lot of discussion about that.
That's a very good question. I definitely see that to be a low-hanging fruit. There are many emission mechanisms that put a strong upper limit on the emission central frequency, but there are other emission mechanisms that do predict millimeter wavelength, millisecond duration flashes. So I see that to be a worthwhile pursuit to constrain the emission mechanisms to. This may not be the counterparts to the FRBs, but these would be unique bursts that do not necessarily have radio counterparts. Okay, so
there's a written question online that I would like to read out. Not someone has written.
Okay,
yeah. How is the high repetition rate of very active FRBs reproduced in these models? Does Brian at the back hear that? How is the high repetition rate of very active FRBs reproduced in these models? Anyone got a suggestion?
Well, I mean, I think the very active repeaters are somehow special, right? I think that's the only way, because they're super active, and it's some sort of observational bias that we see these very active sources, right? It's not like they're very common. So there's some, basically the argument is there's some sort of special magnetar, there's special configurations of the crust and the observer that in the magnetosphere that makes them hyperactive.
Elias, do you want to comment on this and then take over the next final slide?
Yeah, I can definitely like take it over. I think as Zorwa is saying, like it's a little bit hard to say that these young magnetars can be very, very active. I mean, in terms of subpulse structure, as you can even see from like the elastic modes, I mean, there you might have some imprints. And I think in one of the talks earlier, we heard about like potential QPOs and hyperactive repeaters. And so there may be a connection, but that's something I think that can actually be tested from some of those models. And that's something that I think we definitely should do. And this sort of also brings us over to the final slide, where we are tasked to ask, what can we actually learn with different multi-wavelength or multi-messenger counterparts? Can they constrain directly some of the emission mechanisms? And I think already multiple people, I think throughout the conference, and also just now, Yan-Hong has also raised that point very well. For example, if we look at this particular event shown here on the right, which is very, very narrow in frequency spectrum, can that constrain the precise emission mechanism? Of course, the question is this, in that case, a propagation effect or not? And I think making the distinction of, what's propagation, what's intrinsic, would help us definitely also for this one. Let's say where, even the synchrotron maser mechanism has a very, very narrow bandwidth and cutoff at higher frequencies. And then other things that we've heard and discussed, I think, in great detail is specifically X-ray counterparts and what we can learn from those, especially if we look at the galactic magnetar. We had a really great talk about the system where the thing has a lot of X-ray bursts, but then some of them might be special and maybe they have other properties that may better correlate with the FRBs or FRB-like transients observed from SGR 1935. And so the question is, what can that tell us? And I think one of the things that one could ask for those, given specific models, what's the ratio between the X-ray luminosity and the radio luminosity, which can vary very, very strongly and may help to constrain some of those models. We had a very good discussion initially about what we can do with optical counterparts, let's say from JWST or other sources, or even in Alex Cooper's talk about how those can potentially place limits on the maser mechanism if we catch them early enough. So I think there's a lot of potential. And then there's like two things that we've heard briefly about. I can say a bit more about those as well. Those I think are more with should have more than one question mark. Some of these mechanisms can produce high energy neutrino emission. We just want to point that out. Like for the synchrotron maser, you could have from thermal synchrotron like a photon bath. And then if you accelerate some protons, you could have photohydronic processes and theoretically produce TeV or PeV neutrinos. The challenge is the efficiency for this process is even lower than let's say the radio emission. I think can be as low as 10⁻⁸. And so the fluency that you would see, let's say in ice cube, is well below the detection threshold. But in principle, some of those models could produce that. And then I think we also very briefly heard about cataclysmic models where if you were to associate a subfraction of the FRBs with things happening in binaries, or even associated with gravitational wave mergers, bearing of course challenges with statistical associations between GRBs and FRBs, which so far have been unsuccessful. I think the question is, would that help constrain the emission mechanism? Actually, one thing I can say about that particular part is if you look at the binary dynamics giving rise to specific FRB emission, actually it turns out they trigger very specific different mechanisms throughout their sort of in-spiral time or their lifetime. And so in fact, if we were to see something, we could, I think, not definitely, but at least with high confidence, point to very clear suspects, because different from, let's say, the magnetar case, not everything will happen in unison. There it's more like individual mechanisms that pop in at different evolutionary stages. So they are, I think from the binary dynamics, we can learn something. And I think as we've heard in one of the suggestions, I think thinking about the Jupiter Io system as well, we can learn there, I think might help, I think with those binary models too. And with that, I think happy to open it up for more questions, criticisms and suggestions on, how can we use those tools, or even what instruments are needed or what observations are needed to provide additional constraints that might help with the emission mechanism.
Thanks, Elias. We'll have just a few minutes taking a few comments on questions. Pawan?
Yeah, I just want to, this is Pawan from Swinburne University. I just want to circle back to a couple of points that were made previously in terms of repeaters, hyperactive repeaters being fairly rare. We've seen an explosion of number of hyperactive repeaters over the last year. It wasn't that they weren't there, and then we are seeing them now. It was purely new instruments came up, and therefore we started discovering more and more of those. So my question in terms of like, in terms of simulation, in terms of understanding a broad population of these sources, are there good simulations which are available in order to say how many of these sources could be possible in an ensemble of large number of FRB progenitors, and how can we sort of tie them down to emission mechanism if there is a way through just population synthesis?
So Robert has a comment.
I think Paz Benimini had a recent paper. He says that, or he found that the most active repeaters have a lower source density than less active repeaters. It's something like Zipf's law, which is like a law in statistics, or empirically, it's a law in like number of frequency of words, for example. It seems like the more active you are, the source density is rare. So you're seeing some sort of tail of a distribution is what I get from that. You're seeing a very active part of a tail or distribution.
Yeah, so one way to approach that is through this population approach that you just mentioned. But there's also this open question, I think, in the magnetar theory community on how long it would take for the magnetosphere to get back to its original state that is required to emit multiple bursts. I think that's still a very open question within the magnetosphere community. So these hyperactive repeaters, they put strong constraints on and challenge the different time scales that we have in mind for how long it takes for magnetosphere to retain or come back to its position. Yes, an online, Yon Hong.
Oh, hey, I think my comments are follow Elias' several points. Is that okay? It's not about.
I would appreciate if you have just one or two short comments.
Oh, yes. Yeah, let me make it quickly. So, since
thanks.
One important question is whether the narrow spectrum is coming from the intrinsic radiation mechanism or propagation effects, right? But the FAST telescope detected several thousand bursts, even several hundred bursts per day. Nearly all bursts, if we look at then use a Gaussian function to fit, the delta nu of nu is very much smaller than 1. And you will see each burst upper limit or lower limit is very different from each burst within millisecond time scale. I would say it's very hard for propagation effects to do this within millisecond time scale to change the absorption or some frequency to absorb the corresponding frequency. The second one is if we look at the shock structure, even we assume at each point is monochromatic emitting due to the high latitude effect, this will naturally broaden the spectrum, the whole spectrum. So the delta nu over nu has to be larger than roughly 0.58. So this is also contrary to what we see. But for the crust physics, this recent paper I wrote with Ashley, almost done. We just found the elastic waves propagation inside the crust. It's not like all frequency can escape from the magnetar. There are some lower limit, there are some upper limit related to some physics. And the final point is, I see this slide mention neutrino emission. There are actually two papers. The first one is written by Brian Metzger. He calculated the shock to see how the P gamma interaction to produce neutrino. And then the second paper is I wrote with my advisor Bing. We also calculated the if the P gamma interaction happening in the magnetosphere. We just look at the FRB 2004, the galactic one. Since we know there's X-ray, so we can calculate how many gamma we have. But we found for 3 scenarios, magnetosphere, current sheet, or shock, the upper limit of the flux, the maximum flux is still below the ice cube sensitivity. So it seems there's no way to detect the neutrino.
Exactly.
It's roughly magnetosphere. It's roughly 4 order of magnitude.
Exactly.
Below the sensitivity.
Exactly.
Yeah, so it's not possible to detect ice cube high energy TeV to PeV neutrinos from extragalactic tens of megaparsec FRB sources. The one way is through galactic systems, and if there's a 1806 like giant flare that also produces an FRB, and if the flare is propagating nicely along the direction of our line of sight, then that is the hyper optimistic scenario where you could expect neutrino signatures. Okay, great. So I've got nudges from the organizers that we are way past time. Thank you so much, Elias and the online participants. And thank you also. So we will continue discussions over lunch. And hi, Elias. Thank you so much.
Well, thank you, Navin, and everybody.
Yeah, we couldn't spend some more time on this last slide because it looks like we ran over time.
Oh no, that's fine. I mean, I see we're already like almost 10 minutes over. But I think it was a really, really good and lively discussion.
Yeah. Thank you so much.
Well, thank you, Navin. Thanks, everybody.
Bye. See you.